Hello, good morning, everyone. I hope I'm audible to you, all of you. Welcome to the second technical session on National Workshop on Recent Trends in Geosciences 2023. So today we have an eminent speaker, Dr. A. Nallapreddy Garu, ONGC. May I request Professor Jayaraj Garu to read out his biodata. Please, sir.
Morning. Could you hear me? Hello. Could you hear me? Thank you so much. Very good morning to everyone. We appreciate your support for joining the second day as well for this 5-day national webinar launched yesterday. And today we are so glad to have one of the eminent speakers, Professor Dr. A.N. Reddy. Dr. A.N. Reddy is an icon of geosciences in Indian subcontinent. He has a rich experience of over 40 years for his belt in both research and developmental activities on micropaleontology, biostratigraphy, sequence stratigraphy, and on and on. He has published more than 60 research papers in journals of international rapport. He did his master's and PhD in Sri Venkateswara University, Tirupati, Andhra Pradesh. Later, he joined ONGC, one of the prestigious institutes, to work as a geoscience specialist, and he served that organization over 3 decades. The most coveted position in the company everybody would like to work for is ONGC. So he was a leader in dating the sediments by applying micropaleontology and some of the techniques. He has guided many students to complete their project work, MTech, Masters, and doctoral degrees in core areas of biostratigraphy, sequence stratigraphy, and sediment deposition modeling, coastal ecology, pollution, and so on. He worked with Professor Gertrude Keller, one of the eminent researchers from Princeton University, the most prestigious university in the world, USA, especially to throw some light on the extinction of dinosaurs. Along with Professor Gertrude Keller, Dr. A.N. Reddy, and others, have came out with a conclusion that the extinction of dinosaurs was just because of the volcanic eruption that took place, that is considered by Deccan traps. And Dr. A.N. Reddy, although he works for a company, he worked for a company, but still he has a lot of passion and bent towards the academic arena. He's a mentor for many students, including mine. And of course, Dr. A.N. Reddy and myself both worked under the supervision of Professor K.R. Reddy. Dr. A.N. Reddy was the first PhD student of Professor K.R. Reddy, and myself the last student. So this is how our association goes. And Dr. A.N. Reddy is an eminent researcher, and he can talk on any topic related to paleontology and sequence stratigraphy and on. He has a vast experience in delivering lectures across India. Now, may I call upon Dr. A.N. Reddy to deliver his talk on this day. Thank you so much. Dr. A.N. Reddy, please.
Thank you. Thank you, Dr. Jayaraj. Hope I think you are able to get me. It's audible? Hello. Is it audible? Hello.
Sir, audible,
Sir,
sir, audible, sir.
Yeah, please. So, good morning to everyone, and good morning to all those participants.
Thank you for giving me the privilege.
I think I can go ahead with the presentation, no, straight away. Hello. 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 Hello.
It's okay.
I am not able to get any response. Unless you say that yes.
Yes, sir, audible, sir.
It's audible, no? That's why no, I need, because for the first time I am speaking directly not to the audience. So first time I am speaking with the monitor. So these are the problems. However, I think I can go ahead with presentation.
Yes, sir.
Yeah. Good morning to all the participants. And the topic, of course, is very much displayed here in my slide. That is on sequence biostratigraphy, an advanced tool in hydrocarbon exploration. I am sure, I think many participants possibly they are introduced to sequence stratigraphy or biostratigraphy. And if they are introduced to this particular discipline, I think it will be easy for them to really to understand what I am going to speak. However, of course, I will try my best to simplify what I am going to speak on this particular workshop. So, sequence biostratigraphy is nothing but is a biostratigraphic approach to sequence stratigraphy. So, sequence stratigraphy is one of those 21 stratigraphic frameworks. In fact, this is the latest, and it is very widely used in the hydrocarbon exploration. So, because why it is advantageous over other stratigraphic frameworks? Because in sequence stratigraphy, the advantage is you can predict the gaps, especially the unconformities in the stratigraphic record. That is one advantage, major advantage. The another advantage is also we can predict the phases, especially the litho phases, especially reservoir and source rock phases, away from the known point. That means away from the normal. Of course, in the oil industry, we would drill the wells. No, we can't afford to drill so many wells. Maybe we'll be able to drill one or two, and based on that, those one or two reference wells, we should be able to predict which way we should move for a better reservoir development and all. So that is how sequence stratigraphy is very useful and advantageous over other stratigraphic frameworks. So stratigraphy, of course, I think everybody is aware of it. Stratigraphy is nothing but ordering the rock strata in their natural order. So putting them in their natural order means the bottom one at the older one at the bottom and the younger one at the top. So like so this stratigraphy is followed, of course, follows the Steno's laws of principles. So there are four principles. The one is the law of superposition. Of course, that is the oldest and most used, and it is best used actually. So it's nothing but the old is at the bottom and the young at the top. Then comes the law of original horizontality. When the sediments are deposited initially, so obviously they are deposited parallel to the depositional surface. That means they are horizontal. But post-depositional, they can be tilted, they can be folded, they can be, of course, a lot many changes can take place, but originally they are horizontal. So the third one is the lateral continuity. When they were originally deposited, if there was no obstruction, obviously they spread this rock strata they spread in all the directions and parallelly. If there is any obstruction or maybe some erosion or something, then there will be a discontinuity. Then fourth one is the law of cross-cutting relationships. This, of course, you can see here, of course, the A and B are older than the volcanic inclusion, which is the C. So this is how the stratigraphy works to determine which is old and which is A. So that is the primary objective of the stratigraphy. Next. When it comes to the sequence stratigraphy is the latest stratigraphic framework, which is very widely used in oil industry. Because there are advantages I told you just now. So sequence stratigraphy was first done in 1977 by Exxon Mobil Oil Company under the leadership of Whale. So, and that the sequence stratigraphic framework was originated from the seismic data. And before that, of course, in 1963, Sloss has done he was the first person to use seismic, what is that, this sequence, the term sequence, and he has also identified 6 mega sequences in the Phanerozoic of the Northern America. Of course, they are the first order sequences, they are mega sequences. And the Exxon model, of course, is very widely used in the oil industry. And in fact, we have followed, especially this particular model in our study, and which I am going to present today. So what is sequence stratigraphy? Sequence stratigraphy, of course, you can read out, you can know. But in simple terms, to say that this is nothing but subdivision of the rock record into genetically related packages bounded by unconformity surfaces or their correlative conformities or surfaces, you can say. So what is meant by genetically related here? So there are some new terminology, like this, say genetically related. Genetically related is nothing but the strata which follows the Walther's law. Then what is Walther's law? Walther's law, of course, I will tell you the example. It's nothing but, suppose there is a sediment A, which is succeeded vertically by sediment B. And between sediment A and sediment B, there is no gap, means there is no unconformity. So then sediment A is also horizontally succeeded by sediment B. So sediment B in some direction, not necessarily that it is there in every direction. So that is what genetically related means. So the fundamental, the unit in sequence stratigraphy is a sequence. So sequence is nothing but it's a conformable succession, again, which is genetically related and bounded by the unconformities or their correlative conformities. This is the fundamental unit. Like in lithostratigraphy, fundamental unit is the formation. In biostratigraphy, the fundamental unit is biozone. So similarly, in sequence stratigraphy, the fundamental unit is sequence. This sequence is further subdivided into system tracts. System tracts are the contemporaneous linkage of depositional systems, actually. Of course, we have the definition also here. System tracts are composed of all deposits accumulating during one phase of relative sea level cycle and preserved between specific primary chronostratigraphic surfaces. The sequence in marine conditions or in marine the basins is actually deposited during one complete sea level cycle. One complete sea level cycle means here, which represents one transgression and one regression. So that is one complete sea level cycle. So system tracts are the contemporaneous linkage of depositional systems. And the depositional system is laterally linking the lithophase, 3-dimensional lithophases. That is the depositional system. Next, yeah. Because I thought, no, directly I do not want to go to my presentation. So I thought some of the people, the participants, they might not be having any, of course, introduction to the sequence stratigraphy. And I thought, let me, of course, have some introduction to the people, those who are not really introduced to sequence stratigraphy. So what is sequence stratigraphy? Like sequence, the stratigraphic principles we have spoken about, about there are 4 principles like. Similarly, in sequence stratigraphy also, the principles are basically, the principles are those that govern the creation, filling and destruction of the accommodation space. Accommodation space is nothing but the space which is available for the sediment to fill in the any sedimentary basin. That is the, so that is the accommodation space. Then comes to the, just I'm not able to move the slides. Yeah, properly. It's okay. So if you see this particular diagram, so the accommodation is there, no? Just now we spoke about what is accommodation. This accommodation is controlled. That means the creation, filling, and the destruction is controlled by 3 mechanisms. That is eustacy, sediment supply, and tectonism. Eustacy is nothing but eustatic sea level. In a marine environment, it is sea level. If it is a non-marine environment, then climate will come in that place. Then sediment supply, that is the rate of sediment supply, and tectonism. Tectonism is a crustal level disturbance like the uplift or subsidence. These 3 together, they control the creation, filling, and destruction of the accommodation. At the same time, these 3 mechanisms also interact to produce stratal patterns and their terminations. These stratal patterns are nothing but the sediment architecture, that means the geometry of the sediment, the strata, which are actually controlled again by these 3 mechanisms. These stratal patterns are the basis for identifying the sequences, sequence stratigraphic surfaces, system tracks, and parasequence sets. So sequence is the fundamental unit of the sequence stratigraphy. We know that. So for that, in sequence stratigraphy is the main basis, like in lithostratigraphy, lithology is the main basis to identify the lithostratigraphic units. In biostratigraphy, biozone is the fundamental unit to identify the biozonation. And the same way, stratal patterns are the main basis for identifying the sequences and the system tracks and parasequence. There is a lot of disturbance, I think. Hello. 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 So, madam, I am not able to move the slides. Hello. Yeah. So if you see this particular the diagram, so just now we were of course defining what is sequence, and sequence is deposited during one complete sea level cycle, which represents one transgression and one regression. Of course, you can see one regression and also one transgression. During this time, from here to here, this is the time during which, of course, there is a falling limb, and rising limb is a falling sea level, is a falling limb, and also the rising limb, the transgressive phase. During this time, the entire sequence is 1/3 order sequence is deposited. So we were talking about the stratal patterns, Yeah, I think there is some problem. I think it's not able to move the slides properly. Doesn't matter. You can see these are the 3 primary stratal patterns or stacking patterns. And here, if you see the top one, this is a progradational parasequence set or progradational parasequence, where the rate of deposition is greater than the rate of accommodation space. As a result, what happens? The faces move towards the basinal side. Means, of course, you can see that the bottom one and the top one, if you see, this has moved further into the basinal side because accommodation space is less. Therefore, the depositional phases, they are pushing into the basinal side. And if you see this, this is retrogradational or transgressive parasequence set, actually retrogradational parasequence set. If you see here, when the sea level is rising, that means accommodation space is more than the sediment supply rate or rate of deposition. So as a result, the facies belts move backward, that means into the landward side or basin margin side. At the same time, there is a third one, which is upgradational. In this case, the rate of deposition and rate of the both are equal. In such a case, the faces, they upgrade actually. They do not move either in the landward side or in the basinal side. They just upgrade. That means move vertically. So based on these three para sequence patterns, so 4 system tracks have been identified. And also these system tracks, they have a definite place within the sea level cycle. So they have a definite place and they occur only during a particular time period of that sea level change. So if you see here, the low stand system tract, which is the bottom one, the bottom of the low stand system tract is bounded by a sequence boundary. Sequence boundary is nothing but, of course, the unconformity surface or a correlative conformity surface. Is on the landward side, there will be erosional surface, that is a unconformity surface. The same, its equivalent in the basinal side will be correlative conformity, along which there is no any break in time or non-deposition. So the upper bounding surface of this system tract is a transgressive surface or a maximum regressive surface. You can use any one of these terms. So that means when the sea level falls, that means during the regression, this low stand system tract is deposited in the basinal side. And when the sea level starts rising, this is the beginning of the sea level rise onto the shelf. So that's why we call it as a transgressive surface. So this is the base of the transgressive system tract and bounded by the maximum flooding surface. That means when the sea level reaches maximum and encroaches maximum land, that is the highest sea level, during which time the transgressive system tract is deposited and finally terminated by the maximum flooding surface. And this maximum flooding surface becomes the base of high stand system tract, and the upper surface of the high stand system tract is the basal surface of forced regression or BSFR. Of course, this system tract was not there earlier. Now, of course, recently it was introduced. Otherwise, only these three were there earlier. To begin with, Whale and all, they have introduced only 3 system tracts. Now the falling stage system tract is also created now. And the end of this falling stage system tract is a sequence boundary. So in any given sequence, hello, slides, I think they're getting stuck. I'm not able to.
Sir, you just hint us to go to the next slide so that we can operate, sir.
Yeah, please go to the next slide. Yeah, that's better, I think. That's
Yeah,
better.
thank you, sir.
Please go to the next slide.
Share the slide, we will do that.
Please go to the next slide.
Okay.
That will be much better because here I think there is some problem. Can somebody, yeah, you just see here, of course. See how the faces belts are moving with respect to each system tract. If you see the falling stage system tract, actually, this one, the falling stage system tract is the beginning of the sea level fall to the end of the sea level fall. During that time, the falling stage system tract is deposited. Of course, these are not very clear. If you see this here, this falling stage system tract is, of course, developed during the forced regression. That means when the rate of sea level fall is greater than the rate of sedimentation. So in such a case, the facies belts move very rapidly into the basinal side. You can see here, of course, they move very rapidly into the basinal side. This is a forced regression. So once the sediments moved into the basinal side, then they start upgrading in the in the basin as a basinal floor fans actually during the end of the sea level fall. You can see here, of course, these are getting deposited as upgradational and progradational phases in the form of LST. So this is the end of the sea level fall. When the sea level starts rising again, then transgressive system tract is deposited, and you can see that transgressive system tract. During this time, what is happening? Sea level is rising. As a result, facies belts are pushed backward. That means towards the landward side. Therefore, you can see the facies, from bottom to top, they are moving landwards. So during HST, that means when the sea level has reached the maximum, that is the maximum flooding surface. During that time, sea level is either still stand or there may be a slight fall or very slow fall. During that time, this HST is deposited. So during that time, if the sedimentation rate is little more than the whatever the accommodation space is created by the relative sea level fall or the rise or still stand, so that space is filled up with the sediments, and they will be, because sedimentation rate is little more than the accommodation space is created. As a result, the faces move, that means they prograde and they move into the basinal side. But during HST, invariably sediment is deposited only in the shelfal area, but it's not falling into the basinal the side. That means into the actual basin, like in the FSST and LST. Next slide, please. Next slide. Hello. Next, yeah. This is enough. You can see here, of course, this is of course much more, of course, useful. If you see this, this is a shelf and slope profile actually, and the sea level is at fallen just below the shelf edge. Here you can see that means exposing the entire shelf for erosion. So this is all exposed, and also you can also see some incised valley fills which are formed during sea level fall, especially in the coastal region. So these incised valley fills mainly forms where there is a variation in the gradient. So wherever there is a variation in the gradient, these incised valley fills will be there. And they may be up to say 20 meters, 30 meters, 40 meters, depends, of course, depend upon what type of substrate is there. Accordingly, it will be there. And they are very, very important for the petroleum, the hydrocarbon, the accumulation point of view. So we will be talking about this later, how important they are like that. And you see, that time, so the entire area, that shelf is exposed here. There is no accommodation space at all. Now the sediment, all the sediments are moved down into the basinal side. See, now as the sea level is rising, now this sea level here is, it is just on to the shelf edge now. So therefore, this is called transgressive surface, or we can also say the maximum regressive surface, because this is a regressive deposit. End of this regression, the top of this regressive surface, the deposit is known as the maximum regressive surface. And also this is the first transgression onto the shelf. Therefore, it is also known as the transgressive surface. You can see now the next, as the sea level is rising, you can see this, the facies belts are moving onto the landward side. They are the retrogradational phases or a transgressive system tract. You can see now during that time, this particular IVF inside the valley fill is filled up. So initial rise, obviously it is filled with coarser clastics, but later TST, end of TST, there are only finer clastics deposited here in the deeper part of the basin. Therefore, it will be finer clastics at the top of it. The reservoir is below, and the cap rock, which is the finer clastics, and which is capping that reservoir. So therefore, they can be a very, very good reservoirs. And when the sea level reaches maximum, this surface is known as the maximum flooding surface. So then the sea level reaches the maximum flooding surface, and then by the time the sea level starts falling, and the sea level is not falling immediately, of course, if there is a forced regression, then it can happen like this. Otherwise, what is happening? There is a space in the shelf region. Therefore, the HST develops. but during that time, the sedimentation supply rate is little more than the accommodations space. So therefore, whatever accommodation is created by slow fall of the sea level, and that is filled up by the your sedimentation supply. Therefore, HST is developed on the shelf. TEST and HST, they are always on the shelfal side, whereas the LST and FSST, they are in the basinal side. You can see here. This is the complete sequence you can see. So you have the LST, then TST, then HST, and this is a sequence boundary. And also the end of it is again is a erosional surface. Now, because there is no more accommodation here, this surface is exposed to the atmosphere. Therefore, the erosion will take place along this. And whatever the sediment depot centers, now they start directly moving onto the shelf beds and then dump the entire thing into the slope like this. So this sediment invariably it's a reworked sediment in this one. So this will be predominated by the soft, especially the clays and the finer clastics. And whereas your HST is predominated by the sands. Next slide, please. So that is a brief about the sequence stratigraphy and sequence stratigraphic principles and also the terminology and all. So now we will be using that. So we will be using those terminologies and all. Now we are trying to approach sequence stratigraphy using the biostratigraphy. Biostratigraphy is the study of, it's based on the fossils. They're fossil events. Like, the fossil events are basically the first occurrence of a particular fossil and the last occurrence of a particular fossil. That means these datums, these are called fossil datums. So these are the main basis for a biozonation. So we use the fossil events for recognizing the biozonations. So in which is in fact in core, especially the oil industry, biostratigraphy is a core group actually. In fact, we play a very big role in the oil industry because biostratigraphy is close to time stratigraphy. So when you are drilling, especially in the offshore area where you have monotonous lithology, in such a case, especially the seismic reflections will be very chaotic and they will not be continuous. In such a case, you really do not know then how to correlate. So therefore, you require biostratigraphy. So that's why biostratigraphy is very good in the oil industry. In fact, biostratigraphy is surviving because of oil industry. So it provides an independent basis for age dating. This is very, very important. See, geology is nothing but the sum of time and depth or thickness. The stratigraphy is nothing but a sum of the time and depth or time and thickness. So the age dating is very, very important. Is in fact this urgent requirement. Otherwise, you simply cannot do anything. You can't go ahead with the stratal correlation if you don't have the age dating. Then the advantage of this fossils is another one is the paleo water depth. So we can determine the paleo water depth during which time particular say reservoir rock or for that matter any rock, when under what conditions, under what water depth it was deposited can be known. And also we can also identify the paleo environmental. That means especially whether it is a shelfal condition or is it inner shelf or middle shelf or outer shelf, like that environment also can be inferred. And therefore, the stratigraphy, especially biostratigraphy, is very, very crucial and is a core group in the oil industry. So in petroleum industry, biostratigraphy has multifold applications, both in exploration and development stages. So exploration stage is the stage. So we know that particular area is prospective, but we haven't struck in hydrocarbons. So when you are going to prove there are hydrocarbons, that type of activity is known as the exploration activity. The development activities, once it is proved, then you are producing that whatever they accumulated or the hydrocarbons. So during that time also we require biostratigraphy. Biostratigraphy actually it is there right from exploration, development and even reservoir stage also. It is very useful. So main advantage of these biostratigraphy is to arrange strata in a proper sequence stratigraphic framework by facilitating stratigraphic correlations based on seismic and well logs. See, seismic gives the skeleton actually. Skeletal framework it will give, because seismic is a must. Without seismic, you cannot do any exploration, because it is a fundamental data, seismic, because it covers the very wide, see, the entire basin it can be covered. And also the resolution is also very high when it comes to the well logs. After drilling the well, then we actually, there are some geophysical the tools, they will be lowered, and then continuous recording of the entire this lithological succession will be for various things, like a density log, then resistivity log, like many logs are there, they can be recorded. So they can only, this remote sensing data can give you a skeleton, but biostratigraphy gives the life to that. So then only the skeleton will stand up and start moving. Otherwise, seismic and well logs on their own, they are of not much use when you don't integrate with the biostratigraphy. So the correlation of strata in intraslope basins, especially this is very, very important. I will show you because we have an example here. So we were talking about the law of lateral continuity, is it not? Say law of lateral continuity, as long as the strata are continuous, it becomes very easy for us to know that this is the strata which is continuing there also. Suppose they are broken in between because of the shale bulge or the faulting or whatever it is, In such a case, then how you can take a particular the stratigraphic that strata across that and then try to link with the other one. It's with its equivalent one. That means how you can correlate these two different surfaces. So in such a case, biostratigraphy comes for what is that great help. So I will show you that we have a very good the example for that. And estimation of sedimentation rates and structural process within sedimentary basins, of course. Sedimentation rate of sedimentation can be calculated. For that, you need to have the age dating is required. Without that, from one point to the other point, what was the time taken, then only, and what was the thickness of sediment was deposited during that time, that can be calculated. So many centimeters per 1,000 years, like that you can calculate. And also the structural process, especially the like the structural traps, or the stratigraphic traps, when they were actually formed. So again, the dating comes into picture, because we should know that before whatever the hydrocarbons have migrated, before that structure should have been available. Then only it gets into that. Otherwise, it will not. Next slide, please. Yeah. So we are talking about the biozonation, which is fundamental in biostratigraphy. Of course, you can see this is mainly based on the first appearance or last appearance of the particular, suppose here the CF4, CF3, CF2, these are all the zonal, the what is that, names of the different zones. Also the R fructicosa or CF1, what is. So I will just tell you a few things here. The CF4, how it is identified based on the first, that means biozonal bottom datum is based on the first occurrence of Racemiguimbalna fructicosa. Then top of it again based on the first appearance of the P. hariaensis. You can see here. So this is one zone. So when this can be, even it is correlated, of course, here anyway, this time is not given. Otherwise, this can be correlated with the, of course, all these events are radiometrically dated also now. We have a time scale for that. So we can easily know the first appearance when in a geological time when it has occurred, when this has occurred, what is the actual secron, this is called CF4, that means the time span of CF4 zone can be known. So this is very important for us. Once whatever the stratigraphic column you have, once you have studied, then it's possible for you to erect this biozone. So this is a standard biozone. In fact, it is for a GSSP section, the LCF section, I think, Tunisia. Next slide, please. Next slide. Next slide, please. Can I get this next slide? Hello. Yeah. Thank you. Thank you. Yeah. Here you can see, there is a in a particular study, this you can see the hiatus here. That means this particular zone is missing here. So in sequence stratigraphy, sequence boundary is what is that? It is nothing but a unconformity surface. That means there is the continuity is missing here because this is absent. So in biostratigraphy, once you have done this biostratigraphic zonation, whether there is a continuous zonation is there, because we are trying to compare with the Geosciences section where there is a continuous section, or anything is missing. See, here is missing actually here. That means this is the sequence boundary here. This is the sequence boundary. And also you can see your datum events. You see you have the Egyptiaca is a first appearance, then Hexacamerata first appearance, whereas Linnaeana is the last appearance. So for that is age is also there. Now you can see for every event there is also age. So that is how biostratigraphy is much more useful than other stratigraphic frameworks, because it gives you the very close time stratigraphy. Next, please. Next. Yeah. Now, how, of course, biostratigraphy helps in the sequence stratigraphy. See, especially one is the dating we were talking about. This is utmost important, dating of the surfaces, sequence stratigraphic surfaces, and also the sequence stratigraphic units. That means sequence stratigraphic surface, like you say, sequence boundary, maximum flooding surface, then maximum regular surface. So you can, based on the fossils which are present in that, can be used, and then the particular time that dating can be given. So why this is required? It is mainly required for the correlation purpose. The sequence stratigraphic models are based on relative chronostratigraphic framework, which requires a robust biozonation. That means if you have done your biozonation properly, so that will be very, very useful for the time correlation of the sequence surfaces. Next, please. Next. So maximum flooding surface. So maximum flooding surface, that means that is the maximum sea level at that point of time. Then your sea level has occupied the encroached onto the land, maximum onto the land. During that time, your water column, that means your sea level column is the maximum. So the floating animals, especially the, here of course we have done mainly the foraminifers actually. There are a number of microfossil groups, about 20 odd microfossil groups are there. But the best is of course only the foraminifer. That is of course it's a universal truth. Among all the microfossil groups, when it comes to the of course biostratigraphic application, foraminifera is the best. There is no doubt about it. So invariably, out of 100 paleontologists, 90 people will be working in on this foraminifer group only. So maximum water depth means obviously there is a maximum abundance of the foraminifers, both planktics and as well as the benthics at that point of time. So therefore, it is very easy to pick this particular surface. Even the outcrops also, especially in the Relur outcrop in the Kaveri Basin, there is a very beautiful surface which is exposed. There is a Griffia one bed, about 1.5 meters bed is there. There in that was deposit. That is a perfect example of this maximum flooding surface, where you can see hundreds and thousands and in fact millions, you can say rather, very well developed Griffia is present in that. So next, please. And sequence boundary recognition. Just now I have shown that missing of biozones. Wherever once you have erected the biozonation for the entire studied stratigraphic section, then you can try to look for this, anything is missing. Then based on that, you will be able to identify the sequence boundary. That means missing biozonation is the clue for identifying the sequence boundary. Next. And the system tract characterization. Now we do system tract characterization, like this transgression systems tract and high stand systems tract and low stand systems tract. So we know that low stand system tract is deposited during the regression. When the entire shelf is exposed, the sediment is now pushed into the basinal side, into the deeper side of the basin, that means into the slope. During that time, what happened? Your entire shelf is exposed. No, that means the older sediments are exposed. Then they are subject to the erosion and they will be moving along with the whatever the agent which is bringing a river or whatever it is, then entire, so the multiple that sources of the sediment will be dumped into the basinal side in the form of the LST. So therefore they are called mass turbidite flows or mass gravity flows, like that. So if you see the faunal content in that, it is heterogeneous. Next, please. Yeah, of course. Then when it comes to the you can see here also, there is also paleontological characteristics of the system tracks. When it comes to the transgressive system track, that means when the transgression is taking place, then your water column is increasing. As a result, the basinal side only the pyroclastics are getting deposited. Therefore, the organic content is increasing in the bottom. And because of those conditions, so a particular type of foraminifera only they will be able to manage, they will be able to tolerate that the high nutrient conditions and also the increased water depth, and they will be able to colonize and dominate. So therefore, diversity will be very less. Only a few opportunistic taxa will be dominant. But when it comes to the high stand because that is the beginning of the sea level fall. Therefore, the oxygenation conditions are better at the bottom, on the sea bottom, and also the organic content is not that much like in transgression system track. Therefore, the diversity will be more, and the more diversity will be there compared to the transgression system track. Next. Yeah. This is the actual study now. In fact, the case study from the Krishna Godavari Basin. So, in fact, this is the first ever study on sequence biostratigraphy from India, and which we have done first in ONGC only. And myself and my colleague, Dr. Jayprakash, we were the first people to, somehow we were very passionate. We could understand the basic principles of this sequence stratigraphy. We thought, we used to think that definitely we should work on this, and fortunately we got a, next slide you just show me. Fortunately, we got an opportunity when the director exploration has given a project that time to the Chennai. So the Krishna Godavari and the Kaveri Basin, these two basins, they are studied only in the Chennai laboratories. So I was in Chennai laboratory along with my colleague, Dr. Jayprakash. So we had an opportunity. And in fact, so that time, these wells are not there. Whatever the wells we have studied is GS23-1, GS15-4, GS15-3, and GS15-1 was also there. This also we have studied, 4 wells we have studied. So these 2 wells are on the landward side, these 2 wells are on the seaward side. This we have studied, but anyway, now I am showing only the slides of these 3 only. And all these wells were not there. Of course, subsequently they were drilled. I will tell you when they were drilled. So now these 4 wells actually we have analyzed. 2 I have studied and 2 Dr. Jayprakash has studied. Next slide. Yeah. If you see this 15-4, which is on the landward side, no? 15-4 and 23-1 are on landward side. If you see this here, no? Maybe if you can magnify, I think it will be still good if it is possible. If you see this, no, based on whatever the data we got, this is of course a planktic foraminifera, this is benthic foraminifera. If you see the frequency of the planktic foraminifera, no, which is fluctuating, is it not? There is a peak here, and also there is a peak here, and all, of course. So if you see this, these are the foraminiferal events. Based on this, it's possible for us to determine the age. What was the age of it and all. So if you see this, this well has been drilled into the Oligocene. You can see it is drilled into the P21 zone of Oligocene. And also there is unconformity here because missing of biozones. So based on that, we could identify a sequence boundary. And if you see here is about 7 million year, the time is missing here. That means there was a gap of 7 million years here. That means what has happened? Possibly the major sea level fall. As a result, this much of sediment is missing in the shallower side. At the same time, if you see the upper boundary also about 10 million years time. There are 2 major sea level falls in between. Of course, the sequence, which is third order sequence, is deposited. That is called early Miocene sequence. And its age of this early Miocene sequence is something like N7-10-6. Age-wise, if you see 21.5 to 15.5, it's about 6 million years time. This is a secron of this particular sequence, depositional sequence. And if you see this based on the foraminiferal frequency, this is a sequence boundary. And if you see that there is a peak of planktic foraminifers at this point of time, which indicates the maximum flooding surface. And then there is a rapid fall of sea level and ends with a sequence boundary here. And if you see the maximum flooding surface and a sequence boundary, this also merges with the transgressive surface. This is TST, that means transgressive system tract. During that time, there are also some sands developed here, of course, in the TST. Unfortunately, of course, there is some gas also in this. And the benthic foraminifera were also studied, and based on that, we could construct, of course, a broad sea level curve for the well 15.4. So here, what you should remember is this well is drilled through the Eocene-Oligocene boundary, which is important for us. I will tell you when I show the model about the importance of this particular boundary. Next, please. Yeah. This well is 23.1. In fact, it is still towards the landward side actually. But in this case, what has happened? This well, of course, for some reason, they could not drill into that Oligo-Miocene boundary. For some reason, I will tell you why they have not drilled. There was no reason for them not to drill this, but for some reason, of course, lack of the model, they have missed that actually. So if you see this, you can see now that maximum abundance of planktic foraminifera, which identifies the maximum flooding surface. The entire thing is deposited during maximum or the TST, and then you have a HST end of it. Of course, there is a sequence boundary here, of course. And if you see, there are also sands here in this. Is it not? Of course, they are very small in thickness, and some of the sands are gas bearing here. The TST. See, that means TST is gas bearing. HST sands, they do not have any hydrocarbons. In the same case in the earlier well also. Next, please. Next, please. So there is one more well which is on the seaside actually slightly, because there in the 23.1 and 15.4 water depth, present water depth is around say 18 meters, 16 meters. Whereas in this case it is about 30 meters, I think so. Yeah, 30 meters present water depth. Here also what happened? So the well is not drilled through that Miocene-Oligocene boundary, which is very close to that is N5 zone, and N4 zone maybe around 50 meters. If they have drilled maybe another 50 or 60 meters, possibly they could have drilled through that particular boundary. They didn't. And if you see here, of course, the maximum peak, because this we have taken not only plankton, both benthics also. Considering this, we have put MFS here. If you see here in the, there is only one sand in the TST. If you have seen the earlier wells, there are more sands. There are, of course, 3 or 4 or sands like that. But when it comes to the seaside, what is happening? There is only one sand. Why it is happening? Because a transgressive system tract. The transgression is taking place, during which time the depositors are pushed landward side. That's how the wells which are in the shallower depth, they have more sands. Next, please. Next, please. Yeah. So this is the model. Finally, we have sequence depositional model. We have conceptualized. What is model? Model is a probability. Actually, it's not a certainty unless it is proved. Say a model is basically, of course, it's a concept. It's an idea actually. So based on those 3-4 wells data and one well which was drilled much earlier, this data was also available for us. We have used here. Based on these 4 wells, now we have conceptualized the model actually. You see, in all these 4 wells, one well is drilled through that sequence boundary, bottom sequence boundary, which is the Oligocene boundary. There is actually, fortunately, that well has landed into that IVF, incisive valley fill, and it was a gas bearing there in that particular well. It was gas bearing. But when it comes to the other 3 wells, they are just short landed by about 50 meters or about 70 meters or so. They didn't drill through this. Therefore, they failed to assess the potential of this particular surface, which is actually this inside valley fields are there, they are gas bearing. So they have missed this because lack of model. This model clearly explains why we have failed to drill through this. We should have drilled another 50 meters or 70 meters. We could have got into this IVF. So therefore, they failed to assess this particular the potentiality of this particular surface, which is unconformity surface basically. So unconformity is basically is a pathway as well as also wherever IVFs are there, they are reservoirs also. And now all those sands are there only in the TST, is it not? So in this case, there are only one sand actually in these wells. So when it comes to in these two wells, there are 3, 4, or 5 sands are there. That means it's very clear when the transgression is taking place, sands are pushed only backward onto the landward side. That is what model says. So by putting the data in a sequence stratigraphic framework, how easy it becomes for us to see that, to predict the phases. So now we could very confidently said, you go this side, not this side. And everybody was stunned actually how this is possible based on some fossils these fellows are telling like this. But it's true. So we'll see, but how it is true, it's only a model unless until you have some drilling here in this area and prove that there are sands in the TST and they are gas bearing or whatever it is. Then only this model is valid. Otherwise, it's not valid at all. So at this stage, it's obviously it's not valid. It's only just a model. At the same time, so end of that second, that means the top of that 10 million year unconformity is there, no top of HST. Now, so much of sediment must have gone into the deep water, obviously, where the sediment will go otherwise. In 6 million years time, almost 1,000-meter thick sediment was deposited. That means in 10 million years time, the same rate of sedimentation, if you consider something like 1,500 to 2,000-meter thick sediment has bypassed the shelf and gone into the deep waters. So how can we know that unless until we have a drill here? So at this point of time, so we didn't have anything, neither we have wells this side nor this side to prove that this model is, what is that, useful. And so fortunately, we continue to be in the Chennai only. They didn't transfer us fortunately, and we were very much there. And meanwhile, so somehow the explorationists, they got convinced that there is something here, which they didn't even carry out seismic survey in this area, which is actually on the landward side. And somehow they were convinced, and because they went ahead with the acquisition of the seismic data process, and possibly it took for them about 6 months time. And now in second phase, they have drilled some wells in the landward side. Next slide. Next slide. Next slide. Next. You can go to next slide. That is the phase 2. No? See now, so with respect to the 15.4 and 23.1, we told that to go on the landward side. So this is the area we suggested actually. That means in the case of Palli West and also in the case of the Palyam, one place, one more structure is there, slightly this side. This is the area. Now we have studied one well. Palli West 9, this was the well first drilled, and then we have studied this. And let us see what is actually happening there. Next slide. And also remember that there is a, anyway. So see this is actually on the landward side of the 15.4 and 15.1, presented a landward side. If you see here, this well is drilled through the Oligomycin boundary, and also it has entered even into the late Eocene. Even the Eocene boundary is also drilled in this. If you see here, this is a Oligomycin boundary, which is about 7 mega annum, of course, unconformity. And subsequently, if you see, predominantly it's a sandy faces actually. And also you have a maximum flooding surface at this place. You can see now the abundance of the fauna here, both planktics as well as the benthics, because the water depth is the maximum at this point, and therefore we have recognized it as a MFS. And if you see here in the TST, there are how many sands? About a dozen sands are there, and they're all gas bearing. So this is what we have predicted based on our phase 1 work. So this is proved. That means this model, the sequence stratigraphic models are very, very useful in exploration. It's a very clear case. Next well. Next, please. Next. Here actually, by that time already one field, Ravva field, maybe I think many people must be aware of it. which was established, and then we have just now, maybe a few years before, we have already given it to we have privatized that field that time. So then director was interested. Then it's quite interesting here in this, which is the other side of the Rawa. He wanted to know that what's happening in the Rawa field, because Rawa field almost 16 wells or 18 wells were already established for both oil and gas. So he wanted us to study that one well. When we have studied here, the stratigraphy remains same, but when it comes to the TST, here we have more clays, and only HST only we have the sands, and those sands are oil bearing in the Rawa, not TST. There is HST is oil bearing or gas bearing, whatever it is. Because when the sea level starts falling, the depot centers, they have migrated that side, and therefore more sandy the faces were developed in the Rawa area. Whereas in the GS area, more only clay deposits were deposited. That's how there are reservoirs that side. Next, please. We will see the third phase. Yeah, just I will tell you. Now we have seen the model, if you remember. The left side of the model is proved. That means landward side, during TST, more sands are there, and fortunately, they are also charged. Now we have to check the other side, that means basinal side, that means deep water side. That means the sediments which have bypassed the shelf during the end of Miocene nonconformity. What happened to those sands? Whether there were any sands where they were deposited, that we will verify maybe in the phase 3 study. So if you see here, this is a burrow, vertical burrow, is a scolithos burrow actually. These are of course the indicative of shore face conditions. That means very close to the shore face, these sediments were deposited in the Rawa area, where of course we have got the HST reservoirs. No, these are the reservoirs. In fact, these were before our study, and based on the seismic, they were interpreted that they are LST sands, which are basin floor fans and all. But the fossils are telling a different story. So like this. Next. Yeah. What are these? These are actually fossil rain prints. You can see now. They're all of same size. They're our area. Because this happens during HST when your sedimentation rate and your accommodation space, whatever the rate of accommodation space, they are very almost equal. In such a case, sometimes your surface, deposit surface may be exposed to the atmosphere. Sometimes it may be just below the relative sea level. So when it is exposed, you see that exposed portion, possibly that time whatever the rain prints, they got preserved like this. Very, very rare actually. Next. There is one more core. If you see very closely, maybe if you can zoom, you can see there are so many micro faults in this. It is very, very good for the reservoir actually. If more faults means more space, it can more hydrocarbons can charge, then it can produce also more better because of the more permeability in this, in the form of this all these fractures. You can say fractures or micro faults. Yeah. Next. So now we want to see that model now, which is on the landward side. We have seen, yes, it is of course the proving. Now the seaside now. So first time ONGC has taken up a deep water drilling, where water depth is something like, say, this well I think 650, and this well is about 850 meters water depth. So these were the first two deep water wells drilled by ONGC in the KG Basin. In fact, not only in KG Basin, before that in the Kaveri Basin they have drilled one well, but subsequently they were taken up drilling here. Now we have an opportunity to check our model, to verify our model, whether during that Myo-Pliocene sequence boundary, where the 10 million sequence boundary is there. So model says along this particular sequence boundary, so many thick sediments have gone down, that means beyond the shelf edge, and possibly deposited in the deep ocean. That is what model says. We never know. Now we had an opportunity to check how far say the model is right. Now show me the next slide. Next slide. Yeah. So this is one well, KD11 actually, which was drilled. This is about 850 meters water depth. If you see now suddenly, without anything, if you see the stratigraphic column, you can see a very huge thickness of sands are there. So otherwise it is shale, but suddenly all of a sudden there is a huge thickness, about 300-meter thick sandstone is deposited here, of course. In between there are some minor barriers. And now, without of course even dating, so when you have constructed based on the well logs, whatever it is, lithology, there is a huge thickness of, and now subsequently we have studied these wells also for biostratigraphy. Now we want to know that. You see, now whatever these sediments, they must be only the unconformity represented in the shelf. So during that time only they have bypassed here, because there is unconformity, there was no accommodation space. As a result, all the sediments have bypassed. That means these sediments must represent the age of that, whatever the gap is there in the shelf, they must represent only that age. When we have checked that, you see, you can see middle and late Miocene age. That is what is missing there. The 10 million years is nothing but the middle and late Miocene age. So that is the time so much of sediments have gone down into the basinal side. So that means the model both on the left side and the right side is also proved. Next, please. One more well also is there. Two wells they have drilled. This is the first well. Here also there was gas actually. In this sand there was gas. Fortunately there was gas. Next slide. Next slide. Yeah. In fact, one more slide is there before that. There also, because I want to show that there also sands are there. Can you go back one slide back? KD11 and KD12 is also there. No? Okay, doesn't matter. Just go to next one. Go to next one. Yeah. You see, whatever is missing on the, there is unconformity here actually. So during that unconformity, sediments have bypassed and gone down into the deep waters. You see the sands. Thick sands here and thick sands here. Is one of the KD11 and this KD2A wells. These two wells, what is missing is present here. Here there is unconformity, here there is a continuity. You can see now how, of course, the sequence stratigraphic models are useful in predicting the phases away from the known point. That is what the main advantage of sequence stratigraphy, what we have discussed in the very beginning. No? Why we want to do sequence stratigraphy? That is the first question anybody can ask. Next, please. Next, please. Yeah. Yeah. This is the KD11 well. Is a seismic section of that, which is uninterpreted section actually. And somewhere here, of course, there are some sands and they got the, there is a structurization. You can see, here, of course, there is this sand particularly is charged with gas. So just below this, if you see, this one, the entire thing is these reflections are chaotic. That means they are discontinuous. No. Go back. Go back to the slide. I am not seeing the slide. I am not seeing the slide. Hello. Hello. I am not seeing the slide.
1 second, sir. We are operating.
Yeah. So this was the well drilled, and when they got gas, so if you see, here, of course, there is a bulge. Next slide. Yeah. This portion, this portion. There is a shale bulge because the water depth is something like, no, go back. We'll come back to this next time. Yeah, okay, no, leave it like this only. So you can see, here, of course, there is a shale bulge. And there is one more sub-basin this side also. This is one sub-basin like this. And there is one more sub-basin. These two sub-basins are separated by a huge shale push. You can see here, of course. Next one. You can go to next slide. So after drilling this, then this well we have studied for sequence stratigraphy, because our interest is we want to know that whether the sands have gone and where are those sands time wise. So they exactly fit that where the unconformity is there in the shelf, and during that particular period only the sands have reached the deeper waters and they are accumulated here, and fortunately they are also gas bearing. So if you see here, no, this is a sequence bond red one, this is a sequence bond. There are two sequences are identified in this. If you see this N5 is sequence boundary, and also this is N14. At the age, this is of course the N5 is a zone, no, biozone, and N14, not N14, N10 and N11 actually, I think. I'm not able to clearly see this. Of course, anyway, this one biozone, this biozone. And there is a second biozone. This biozone is present in the shelfal region, but this biozone is not present in the shelfal region because this is represented by unconformity there. So during that time, the entire sediment, whatever was coming from the landward side, has been directly dumped into the deep oceans. That's why there is a huge thickness of sands and in this particular deep water side. So after seeing the success of this, the explorationists, they didn't wait for our study actually. So we have done a very good work here, but they didn't wait and they went ahead with one more well drilling here. Show me the next slide. Show me the next slide. Yeah. So this is what they have drilled. Now there's one more well they have drilled in this sub-basin because they didn't want to wait and incorporate this data because it's time taken. They are very much excited. They want to go ahead and then prove that this entire area is gas bearing or whatever. They drill this well, and unfortunately this went dry. Why it went dry? We will tell you. Only we can tell that. Because you see, if you see these reflections, seismic reflections are strong reflections. Because of the shale push, when you want to take this strong reflection to this side, with which reflection you will correlate this? There is always a doubt, because of the shale push. But somehow, so therefore, biostratigraphy data is a must in such a situation. But somehow they didn't wait, and I don't know how they have correlated, and they have never shown their what is that interpretation. And they have correlated with something else, and then they have of course finally drilled and went dry. So now we have, after drilling this, we have analyzed this well again. Just show me the next slide. Show me the next slide. Yeah, this is the, when we are done, then this is a sequence 1 and sequence 2. This is a sequence boundary of the lower sequence, the lower boundary, and this upper boundary, and this is the upper boundary of the second sequence. In this sequence only the sands are there, and which is gas bearing in this case, this one. If you see this, this equivalent is still got this N11, and this is the N11. You see, because of the shale push, how much of variation is there in there? Time wise, if you want to correlate, you have to correlate this reflection with this actually. Then only whatever the map you have made, which is correct. Otherwise, it's wrong. That's why they have gone wrong, and this well went dry. So this equivalent is this time wise. But you may be tempted to correlate with this or correlate with something else if you don't have the biostratigraphy data. So biostratigraphy data, that's what I told you in the very beginning. Seismic will give you only a skeleton, but biostratigraphy, biozones will give you that life to that skeleton. Then only it is properly done and perfectly done. Otherwise, it is only a skeleton. Next, please. Next, please. Yeah. So just to show this, so during transgression, what is happening to the facies belts? You can see, this is predominantly, of course, is a fine-grained sediments, and this is of course the coastal sediments, red. These are the shelfal. Actually, that means when the sea level rise is there, the sea has encroached onto the landward side, and all the sands are deposited only in the shelf and the coastal side. and the deeper part of the basin is filled with only the finer clastics. But when the sea level falls, that is during the regression, you can see entire thing, the entire shelf is exposed here, and the sediments have gone down and got deposited as FSST and LST in this. You can see here. So what we have seen, the KD11 and KD12A, those sands belong to these system tracts. Next, please. So this is another model we have made. There are, of course, here in the slope itself, there are many basins in the Krishna basin actually. These basins are something like 3,000 meter, 3,500 meter deep. Within this slope, there are many basins. And the entire sediment, whatever has bypassed the shelf, got into these basins and accumulated here only. So like that. But each the filling the mechanism varies from basin to basin. Of course, it's not the same in all the basins. That's how in one basin there was gas and another basin there was nothing in this. That was the reason. So they didn't wait to understand what was happening. Next, please. Oh, yeah. So mainly in the biostratigraphy here, we have used only the foraminifera because I know only foraminifera. And also we know that foraminifera are the best. And these are the index fossils. So especially for age dating, we use only index. What is index fossil? Index fossil is nothing but, which is very characteristic. In fact, rather easy also to identify those because they are very characteristic. And they have a very short vertical range. Their lifespan is very less actually compared to other species which are non-index fossils. And also they have a very wide geographic distribution and also show very rapid evolutionary trends. So these are the things advantage of this index fossils. Index fossil, so it's very important in any, of course, the sediments when we study. First, we look for those index fossils so that we can fix the age for it. Then from there we can proceed further. Next, please. And these are the some of the deep water the benthic foraminifers, which of course mainly predominantly here we have the Hoosier nets. Next. And these are the shallow water benthics. In fact, in the LST, what is happening when the sediment is reworking and getting deposited to the deeper side, the landward side, whatever was the sediment, marine sediment was there, which was the shallower water sediment. Those forms also they get into the sediment and finally they dump into the deep waters. That is how it's possible for us to differentiate the LST from the HST and like that. So these were very, very dominant actually, these things. All these things, they are very only in the inner shelf forams. Next. Also, of course, then especially the KD11 and KD21, where the massive thickness of sand is there. No, we don't have any foraminifers in that because they're reworked one and they're all less tried. Then we went for the study of dinoflagellates in that particular section. So here also there is a lot of what is that reworking is there, but still some dinoflagellates which are in situ, we use them for dating of that particular sands actually. Next. Here, of course, phase 2, what we have done, we tried to synthesize both for the KG basin, and that is, of course, Godavari shelf and also the Krishna shelf and Krishna deep water also. So, at that point of time in Godavari, we didn't have any deep water wells. So, these are the only 2 deep water wells. But by projecting this, what is likely happening, how these system tracts are distributed in this area, that we have modeled. Next, please. I will show you that model. Of course, for this, of course, we have taken number of wells, the sections right from Rawa to Godavari offshore. Then next, for making that model, we have used this and this KDA and KD1 and KD2 and also this also where this thick sands were deposited in the deep waters, no, that portion of it. Next. Yeah. So also in one of the wells, actually, this is GS110. It is in the offshore, 250 meters or something in the water depth. there was a core in this particular thinking that there was a sand. They have taken a core actually. If you see this core, no, this heterogeneous lithology, which is an indication of a mass flow or a debris flow and all, which is actually FSST or LST deposit. So we can see clearly in the core. Yeah, next. If you see the phenological assemblage, these ataptanas and alaptanas percentage, especially in that KD1 well. So if you see the more of allopthanous material is there than the atapthanous material. Atapthanous is in situ material and allopthanous material, which is reworked material. There is a clear evidence that all those sands in the KD11 and KD12, whatever we have seen, those sands have been, of course, derived from the shallower, the coastal and shallower shelf. So therefore, they contain a lot of allopthanous material. So like this, we can say that, of course, they are, of course, derived sediments. Next. Yeah. So finally, we have using whatever the wells are there, we try to decipher then the system tracts, both in Godavari and also the Krishna basin. So predominantly in the shelf, present day shelf, and in the coastal region, we have the development of both the TST and HST. And when it comes to the slope and down below, we have, of course, the LST fans, and these are the shelf wedge, of course, they are slope fans and all. So now in this area, actually, this area is being explored now very intensively. Of course, even private Reliance also doing it. In one of the wells, of course, I have studied that ONGC wells only. What are the sediments which are bypassed equivalent to that KD11 and KD2? They are the sands here also, they are producing gas. So that means the sediments which have bypassed the shelf during Myopliocene times, that means where the unconformity is there in the shelf, that time a lot of coarser clastics have gone into the deep water and got deposited in the form of LST deposits. So they are the ones which are gas bearing now. So therefore, you can clearly understand that by doing sequence stratigraphic modeling, it becomes more easier for us to predict the phases and also avoid dry wells and unnecessary spending. Sometimes we are short landing, sometimes we are. Otherwise, you can see in the two wells, especially in the landward side, we have failed to drill into the Myo-Oligocene boundary, that IVF. So there's we have missed those, of course, the hydrocarbons, because by not drilling into that particular surface. Next, please. I think it's the end of it. Yeah. Thank you very much. Hope that it was at least a bit interesting for the people. And maybe those who are really aware of sequence stratigraphy or biostratigraphy, I'm sure I think it was interesting for them. Thank you very much. Thank you very much, madam, and for giving me this opportunity to speak with all the participants. Thank you.
Yeah, thank you, sir, for your detailed lecture. Now it's a time to interaction. Anybody would like to ask questions?
Yeah, please.
They can. Yes.
So there is a question from Jayalakshmi. What is paleo water? There is nothing like paleo water. Paleo depth, actually. Paleo water depth. There is nothing like paleo.
Sir,
Yeah, please.
I'm Professor Raghuval, sir, head of department. Sir. Hello.
Yeah, please.
Sir, does it have any other uses, sir, apart from natural gas and island natural gas?
See, sequence stratigraphy framework can be used in every sedimentary basin, irrespective, of course. But here, only thing is here, the advantage is phases prediction. There is a main advantage in this is phases prediction. That is the main advantage, and also it is giving the chronostratigraphic, that means the time framework to the rock stratigraphy. That is the advantage.
Sir.
And in oil industry especially, of course, the reservoirs are, of course, that is our main target. Therefore, this works well for oil industry. No, many academicians are also doing it, but that's of course application wise. Of course, it may not be, of course, but you can do sequence stratigraphic framework for sedimentary basins. We have done for Kaveri outcrops also. There also it's possible maximum flooding surface because this is predominantly with a limestone. So you can predict that limestone faces with respect to once you have done this sequence stratigraphic framework. That we, in fact, even I think we have done it even the Kaveri outcrops also for that particular limestone. Which side we should move for this flooding surface?
Sir. Thank you.
Thank you. Allochthonous is, of course.
Hello?
Yeah, allochthonous and autochthonous, somebody, of course, they asked. I think I just explained that allochthonous material, which is, of course, coming from the outside, which is not in situ. So that means which is derived from a different source. Next. There's some allochthonous autochthonous, okay. No, somebody said it is instead of simple CSI sequence stratigraphy, biostratigraphy sequence stratigraphy is more useful. Of course, because in biostratigraphic approach, main advantage is age dating. Definitely, it's age dating. It is definitely more advantage.
Sir, there is another question from Surendranath that is there any difference in the carbonate and clastic gases?
Yes. There is a separate carbonate sequence stratigraphy is separate because terminology changes and there is a little basic principle remains same. See, for this can be applied for all the basins irrespective of any environment. It can be applied. Only thing the terminology will change, approach will change. Can be done.
Okay. You can say.
But only thing is, see, unless until you identify the system tracks, no, you cannot do. It will not be useful. Just you can identify the sequence boundaries and sequences. Unless you have identify the system tracks, no, it's not possible for making any model.
Okay. Hope I think Surendranath is clear, sir, by this time. Yes. Next మనం మాట్లాడతాం.
Any more? What is this? Of course, Surendranath, I think, is clear. I think. Only thing you see, it's a problem is you need to have this particular subject in your MSc. If you don't have this, of course, straight away listening to a lecture like this will be difficult.
Yes.
Hello? So,
You
sir,
should have some.
sir, thank you very much, sir.
Yeah, thank you.
Thank you very much for sparing the valuable time and your elaborate PPT, which has shared great information. Hope the participants have got a great knowledge out of your PPT, sir. Thank you very much, sir.
Thank you, Dr. Babu, and thank you, madam. Thank you, Jayaraju.
Thank you, sir, for your valuable time and elaborative lecture, sir. So with this, the second technical session is over, and third technical session will start tomorrow at 10:15 a.m. Tomorrow the talk will be by Professor K.S.N. Reddy Garu, Head Department of Geology, Andhra University. So I request all the participants to gather through the same link by 10:15 a.m. Thank you. Thank you for your cooperation. Sir, one more thing, sir, Nallapreddy, sir.
Yeah, madam.
These PPTs can we share with the students or the
Oh, yes,
participants?
yes.
Thank you,
No
sir.
problem. It's already published work only. There is no problem.
Okay, sir. Okay, sir. Thank you, sir. Thank you and good day, sir. Yes.
Thank you. Thank you.
Now we will wind up the session, sir. Thank you.
Yeah, please.